Okay, so we are happy to have Sebastian Burciu from Institute of Mathematics of Romanian Academy today. He works on tensor categories, quantum groups, Hopf algebras, and representation theory. Today, he will talk about conjugacy classes and Grothendieck ring of premodular categories. Sebastian.
Okay, thank you very much. So thank you for giving me the opportunity to talk today at your seminar. So as Sebastian said, the title is on conjugacy classes and Grothendieck rings for premodular categories. So let me see. It goes too fast. Okay, so just a second. Yeah, so we start with an example. Well, I had two slides. I think it's just a second. So what's going on here?
Presentation mode of your.
No, I think I have this thing. It is too big.
Okay.
And there are two images. Can you see? So maybe I should stop share and.
Okay.
What's going on? Stop share and I'll try again. Sorry about this.
No.
So, but I don't see the PD. So, what do you see now?
So it's a kind of intermediate screen. Yeah.
I have to. Wow, what is just a second. So do you see the presentation?
Yeah.
Just the presentation, not it is okay now.
Yeah, it's okay.
Okay, so I can start. So sorry about this. Conjugacy classes were introduced by Shimizu for fusion categories, and they are extending the classical notion of conjugacy classes for groups. So in this talk, we present some new properties of conjugacy classes for pivotal fusion categories. In particular, we will prove a Burnside type formula for these structure constants. You'll see in a moment the definition of these structure constants. So in the case of the groups, of finite groups, these structure constants are integers. In general, they are not anymore integers, but Zhou and Zhu have proven that for semisimple quasitriangular Hopf algebras, if you multiply them with the dimension of h, then they are going to be integers. So we extend this result for weakly integral fusion categories. So let me remind you the classical situation from groups. So if I start with a finite group G, I can write G as a union of the conjugacy classes. And to each conjugacy class, I can associate the sum of the elements from that conjugacy class. And this element is called the class sum of the conjugacy class. We all know that we form a basis for the center of the group algebra C of G. So when I multiply two such conjugacy classes, the product can be written as linear combination of them. So there are some scalars which a priori are complex numbers for which we have this equality. These scalars are called the structure constants. And in the case of finite group, it's not hard to see that these are integers, just counting how many elements of the group enters in each product. And also a long time ago, Burnside gave this formula in terms of characters for these structure constants. And we should say that from this formula doesn't follow directly that these structure constants are integers. So the only way to see that they are integers is by counting arguments in this formula. So for a pivotal fusion category, we will prove a similar formula, while in a few slides later, we will define the conjugacy classes and the analog of conjugacy class sums. So we should mention that this formula was obtained initially by Cohen and Westry in 2000 for semi-simple quasi-triangular Hopf algebras. Now, also a short history about the structure constants. In the same paper, Cohen and Westry prove that for a quasi-triangular semi-simple Hopf algebra, if I multiply by the square of the dimension of H, then I get non-negative integers. So in general, these structure constants are rational numbers. Recently, Zhou and Zhu have extended this result. Actually, they showed that it is enough to multiply by dimension of H and still get integers. So our result extends this property from quasi-triangular semi-simple Hopf algebras to pseudo-unitary premodular categories. So I remind you, a premodular means a braided and spherical fusion category. So the result is the following. If I have a pseudo-unitary premodular category, if I multiply these structure constants by dimension of C, I get algebraic integers. And also, if C is weakly integral, which means that the Frobenius-Perron dimension of C is an integer, then actually these products are non-negative integers. And also, if time allows, I will present a new result, joint work with Sebastian, that if we start with a pivotal fusion category and have a complex number D such that these structures are integers multiplied by D, then we have a similar Frobenius property, which I call here D Frobenius property, that the dimension of V divides D times the dimension of C. So I should remind you there is a conjecture that in a fusion category, the dimension of a simple object divides the dimension of the fusion category. For the category of representations of finite groups, this result is well known. And Ettingov, and Ostrick extended this conjecture. They formulated the conjecture for any fusion category, and they prove for what now are called weakly group theoretical fusion categories. So the conjecture is true only for this class of fusion categories. So before defining the conjugacy classes, we have to introduce the adjoint algebra of a fusion category. This was done by Shimizu. So let me shortly remind you the construction of Shimizu. So if I start with a fusion category, I can make the dreamful center, G of C. This is also a fusion category, and we have a forgetful functor from G of C to C. This admits a right adjoint denoted by R, and the composition FR is a Hopf comonad, and also it can be defined as an end, a categorical end. for any object V. This is the end of the bifunctor X tensor V tensor X star, and X runs over C. So also for technical reasons, I denote by P of V and X the universal, the natural transformation associated to the end Z of V. So the joint algebra of the fusion category is defined as R of 1. 1 is the unit object of C, and this is this is a central commutative algebra in V of C. By central, I mean an element from V of C, and commutativity with respect to the braiding from V of C. And also the hard braiding of A, which makes it an element of V of C, is given by this formula. Here, delta, I haven't written, is the multiplication of the Hopf common at Z. So delta of 1 is from Z of 1, which is A, to Z of A. Z square of 1, which is Z of A. So first I apply delta on the first component, then the universal projection, and then the evaluation on the last two terms. So in this way, I get the hard braiding. Also, I have a multiplication, which makes it a commutative algebra. I will not insist on this formula. And what we have to keep in mind is that any other object X from C carries a canonical left A module action in C. So I have to define a structure from A tensor X, a module structure. So first I project to the universal natural transformation in X tensor X star. And when I apply the evaluation here on the last two terms, so we have to keep in mind the following two examples for joint algebras. If I start with the category of representations of a finite group, rep of G, when the joint algebra is the group algebra as an algebra, but as a G module the structure is given by conjugation. G data is G8 tensor, G8 G inverse. And also any other object from the category M, we had X before here, carries the canonical action, which is the standard action of M regarded as a G module. So if you have any questions, please interrupt me at any time. So in order to have everything clear. So something similar happens for Hopf algebras. The joint algebra is H itself as an algebra, but as an H module, we have the analog of this conjugation, which is called the adjoint action. And also the structure for any other object is the canonical structure. There are examples, for example, for quasi-Hopf algebras where this structure is different. It's not anymore the standard structure. Okay. Now we have to define characters for objects in a pivotal fusion category. This was done also by Shimizu. So basically, he reconstructs the whole theory, character theory from finite groups. In the case of pivotal fusion categories, the characters are defined as traces, like in the classical case. So we need pivotality in order to be able to define traces. So I remind you, a pivotal structure is an isomorphism, a tensor isomorphism from the identity of C to the double dual star star. And with the help of the pivotal structure, we can construct a field evaluation. The usual evaluation goes from X star tensor X to 1, but here it goes the other way around. So X tensor X star is sent by GX, this pivotal structure, to X star tensor X star star tensor X star, and now I apply the usual evaluation, but at X star. Okay, so having a right evaluation, now I can define a partial pivotal trace. What is this? Whenever I have in the category an arrow from A tensor X to B tensor X, then I end up with a morphism from A to B, which is called the right partial pivotal trace of F. And it goes in the following way. I write A as A tensor 1, I apply the coevaluation on X, so I end up in A tensor X star. Now I apply A tensor F on the first two tensors, so I end up in B tensor X star. And when I apply the tilde evaluation from here, so I end up in B. So in this way, we get a morphism from A to B, associated to any other morphism from A tensor X to B tensor X. Of course, if we put A equals B equals 1, then this is the usual pivotal trace defined long time ago. For any endomorphism of X, the pivotal trace is going to be an endomorphism of 1, which in the fusion categories are just the scalars, C. And the pivotal dimension or categorical dimension of X is defined as the right pivotal trace of the identity of X. So let me see. Now we are able to define a character for any object X in the category. So remember the canonical action denoted by alpha of X for any object from the category. So the action goes from A tensor X to X. So if I take the right pivotal trace that I have defined before, I end up with an arrow from the adjoint algebra A to 1. And this morphism from A to 1 is called the character associated to X. The space of all characters, of all arrows from A to 1 is called the space of class functions on C. And of course, we'll see as an example that in the case of finite groups, we recovered exactly the space of classical class functions for groups. We also have a multiplication on CF of C, which is defined here. Again, we have this co-multiplication of the Hopf comonad. I haven't entered all the details. And here is Z, which is F composed with R is a functor, so I can apply Z of G. So in this way, F star G is again a function from A to 1. This multiplication of characters behaves well with respect to the tensor product. And in fact, Shimizu have proven that by IRR of C, I mean isomorphic classes of simple objects of C. So the character of these simple objects form a basis for CF of C. So basically CF of C, the space of class functions over the complex numbers, or in general over a field of characteristics 0, is isomorphic to the Grothendieck group of the category. So working with this CF of C or the Grothendieck group of the category is equivalent. So Shimizu also defined the space of central elements, which now are arrows from 1 to 1. Remember, the space of class functions are arrows from A to 1. From the way they are defined, there is a non-degenerate pairing between these two spaces, which is given by composition. So basically, if I start with an arrow here from 1 to 1 and one here from A to 1, I get an arrow from 1 to 1, but the space of endomorphisms of the unit is isomorphic to C. So basically, it is a scalar, Z, chi, the pairing between Z and chi. So as I said, well, over the complex field, every fusion category is non-degenerated. So we have this isomorphic between the Grothendieck ring and the space of class functions. So as examples, if I start with a semi-simple algebra, as we expect, the space of class functions is the space of characters, and the space of central elements of the category is just the center of the algebra H. And this can be seen easily by computation. So an H linear arrow from 1 to H add has to satisfy this property from here to be H linear, which means that f of 1 is the central element. And conversely, something similar happens for C of H. So now we can define conjugacy classes, the notions that we will work with. As I already said, this was done, the definition was introduced by Shimizu. So let me remind you the settings. I have a fusion category. R is the right adjoint of the forgetful functor from the Greenfield center. The adjunction between R and F gives a canonical isomorphism from the space of class functions, which is the space of arrows from A to 1, to the endomorphism of the adjoint algebra, Z of C of A and A, which can also be written as the endomorphism of R of 1. And this isomorphism is the one following from the adjunction. So for simplicity, for the rest of this talk, we assume that CF of C, so basically the Grothendieck ring of our category, is commutative. So R of 1 being an object of Z of C, which is a fusion category, can be written as a direct sum of simple objects. These simple objects are called the conjugacy classes of C. Now, this isomorphism is an isomorphism of algebras, where here we have the usual composition in the endomorphic ring. So the central primitive idempotents from here have correspondent central primitive idempotents in the space of class functions. But the central primitive idempotents, sorry, there is question. Hello?
Hello? No.
No, okay. Yeah. So the central primitive idempotents here correspond to projections on the simple summands, which are the conjugacy classes. So if we assume CF of C commutative, then because of this isomorphism, R of 1 is multiplicity free. What I mean by this is any two direct summands here are not isomorphic. So all of the simple summands have multiplicity 1 inside R of 1. So since the algebra C of C is commutative, this is going to be product of the fields. So these are the corresponding central primitive idempotents, and we get this formula. So from here, we see that there is a bijection between conjugacy classes and central primitive idempotents. So if I start with an Fj, by this isomorphism, this corresponds to some tilde Fj here. And this in turn corresponds to a projection on a conjugacy class. So in this way, I have a canonical bijection between the central primitive idempotents of CF of C and the conjugacy classes of the fusion category. So as we expect in the case of finite group, so C rep of G, the adjoint algebra, we have seen it before, how it's defined, and the simple summands are exactly the usual conjugacy classes, well spanned by the complex number. I should have written here C of Cj to be a vector space. Cj is just a subset of G. So what is the bijection from here? We know that the central primitive idempotents of the character ring are the characteristic functions on the conjugacy classes. So basically sends an element G from the group G to 1 if the element G is in the conjugacy class, and to 0 otherwise. So this is this bijection in the case of representations of a finite group. Well, we also need a notion of integral and co-integral for a fusion category. So this generalizes the usual notion of integral and co-integral for semi-simple Hopf algebras. An integral is a central element, an arrow from 1 to a, satisfying this equation. A co-integral is a class function, so arrow from a to 1, satisfying what is called the dual equation here. And as in the case of Hopf algebra, Shimizu has proven that the integral and co-integral are unique up to a scalar. So their spaces are one-dimensional. And as I already said, for a semisimple Hopf algebra, we recover the classical notions of integral and co-integral. With the help of the co-integrals, we can define the Fourier transform associated to a fusion category. So here lambda is a co-integral. To each co-integral, we have a Fourier transform, but this space is one-dimensional. So basically, it is the same Fourier transform multiplied by a scalar. So a central element A is sent to lambda harpoon by S of A. I haven't written the definition of S. This is what is called the antipodal operator, and it generalizes the notion of antipode in the Hopf algebra case. So, and here the harpoon is the usual, it generalizes the usual harpoon. So if I have a class function and a central element, I can create another class function. So B tensor identity of A goes from A to A tensor A. When I apply the multiplication M of A, so I end up again in A. And when I apply the class function, so I end up in 1. So we get a function from A to 1. So in this way, the Fourier transform is defined. Now we can also define the conjugacy class sum associated to any conjugacy class with the help of this Fourier transform. So if I have a primitive idempotent in the space of class functions Fj, the inverse by the Fourier transform of this is going to be a conjugacy class sum. And because of the bijection between Fj and Cj, this class sum Cj also is associated to the conjugacy class Cj. As you expect, they form a basis on the space of central elements. So when we multiply two such elements, we get a linear combination. And these scalars, here it should be complex numbers, also here, because we work over complex numbers. So these scalars are called the structure constants associated to the fusion category. So going back to the example from group case, this Fourier, the co-integral is P1, where PG is the dual basis in C of G star, the canonical dual basis, and this is the formula for the Fourier transform. So what we should mention here that for fusion categories, the Fourier transform it is captured only the restriction of the Fourier transform to the center of the group algebra or the center of the Hopf algebra. So in the Hopf algebra case, one can define by the same formula the Fourier transform on the whole algebra H. And of course, it has values in H star. So in particular, you put H equals C of G in this example. But in the case of fusion category, we recover only the restriction of this Fourier transform to the space of central elements, which are sent to the characters, which live inside H star. So this is the Fourier transform associated to the fusion category of H. Okay. One more result before starting sketching the proofs of the theorems. So also Shimizu has constructed explicitly the characters of the simple objects of C and also the central primitive idempotents, which live in C of C. So first of all, it's not hard to see that A is isomorphic to VI tensor VI star. Well, as algebras, because we all know that VI tensor VI star can be realized as an algebra inside the category C with the help of the duality. So the central primitive idempotents are defined in the following way. You start with 1, take the co-evaluation at VI, so you end up in VI tensor VI star, and via this isomorphism include this in A. And also take chi I from A, via this isomorphism, you project on VI tensor VI star, and then you apply the tilde evaluation here, so you end up in 1. So these are primitive idempotents, and remember the pairing between class functions and central elements. They satisfy this equality where di here is the quantum dimension of vi. I haven't written this. So you recover as in the classical case when you evaluate characters at primitive idempotents. Okay, now we have to move a little bit to something abstract, and then we will make a connection between these two in order to prove the theorems. So in the next slides, I will discuss about probability groups. And for this, I should start first with a hypergroup. Well, some people call these generalized hypergroups, but to be shorter, in this talk, I will call them hypergroups. So what is a finite hypergroup? Is a finite set A, such that if I take the space, the complex space generated by A, this turns to be a star algebra. And if I write A to be C0, C1, Cm, which C0 equal 1, the unit of A. So I always insist that 1 is inside this finite set A. When this becomes a star algebra, the basis A is stable under the star operation. So Ci star also lives inside A. And when I impose some condition on these fusion coefficients, let's call them fusion like in fusion rings. So when I write two elements from the basis, I get a linear combination with these fusion coefficients. And the conditions that I have to impose is that if I look at the coefficient of C0 and 0ij, this is a real positive number if and only if Ci star is Cj, and it is 0 otherwise, if Ci star is not equal to Cj. So these are the identities that we see in the Grothendieck rings or fusion rings. But the difference is that we don't impose these coefficients to be non-negative integers. So they could be any complex numbers as long as they satisfy this condition. So whenever we have a hypergroup, we can define the multiplicity map. While I denote it by P here, you'll see later the reason. So you just multiply the coefficients. We have a linear functional, which on the basis A, sends A to 1 if A equals to 1. So basically, if A equals C0, from the previous notations, and otherwise we send them to 0. So also you can see the town of X is the probability of A of 1 in X. So because we have an inner product on C of A, the algebra spanned by the basis A is always the semi-simple C algebra, having this inner product defined here. So these are all known things. So probability groups were introduced in 1979 by Harrison, and he studied them in connection with other things, but we see that they are also useful for studying Grothendieck rings. So what is a probability group? First, I should give you some special cases of hypergroups. So as you expect, a hypergroup is called a billion if the group algebra generated is a billion, real if all these fusion coefficients are real, non-negative if all are real, non-negative, normalized if in such a product CICJ from here, the sum of all these coefficients in this product where sum is 1. So this is an important definition because we'll also use it in the definition of probability groups. And symmetric if the coefficient of C0 in II star is the same as in I star I. Okay, so a probability group is a symmetric, which means this one, real non-negative normalized hypergroup. So basically, I have written here the additional conditions. The sum of the fusion coefficients in the product should be 1. All the coefficients are non-negative numbers, not necessarily integers. Well, they cannot be integers because the sum is 1. And also we have this symmetry, this condition. For a probability group, we can define the order of an element as being 1 over the probability of 1 in A star, and also define the order of the entire probability group as being the sum of the orders, HA. And N of A is called the order of the probability group. And the usual definition of fusion ring that probably most of us have already encountered can also be given in terms of hypergroups. So a fusion ring is a hypergroup in which these coefficients are non-negative integers, and these coefficients of Ci, Ci star, and Ci star, Ci are always 1. Okay, so now we study a little, this is a kind of technical slide, but I should mention a little about the structure of the group algebra generated by an abelian hypergroup. So since it is a commutative algebra, we have a basis given by the characters, linear characters from C of A to C. This town gives a non-degenerate trace on C of A. So there are some non-zero numbers, and I have denoted them by 1 over nj since they are not 0. Such that town of fj is 1 over nj. So I can write down a sum of mu j over nj. These nj are called formal codegrees in the case of fusion rings. Now it can be seen that we have 2 pairs of dual bases for this bilinear non-degenerate trace. One is given, yes. Are there questions?
No question.
Okay, yes, so I will continue. So remember, HA is 1 over P of 1 in A star. So it is easy to check that these are dual bases for the bilinear form town. And also from the definition here, Fj and Jfj are also dual bases. So having two pairs of dual bases, we have this tensor identity between them. And this tensor identity allows us to give a formula for the central primitive idempotence in C of A. And also from here, applying mu j tensor mu j to this dual basis formula, we see that nj is given by this one. And since HA is positive, because all the coefficients are non-negative and for HA they are positive, we get that nj is always, the formal codegree is always a positive number. Now A hat consists of all algebra maps, linear characters from C of A. It is, of course, a basis for C of A star. The cardinality of A hat is the cardinality of A. Now on C of A star, which coincides with the vector space generated by A hat, we can define a new multiplication by declaring mu I star mu j if we multiply two elements from the basis. The multiplication is pointwise the elements from the basis A. So it means that we can write mu I star mu j as a combination of all mu k's. So we have another fusion coefficients here called the dual fusion coefficients. And also on the dual, at least in the case of a commutative or abelian hypergroup, we can define also a star structure by this formula. Mu j star of A is by definition mu j of A star, which can be proven from star algebra results, is just the usual conjugate of mu j of A. So mu j star, it is also an algebra morphism, and this can be realized as a star structure on C of A. So also mu zero can be defined as the morphism, the linear character that sends every element of the basis A to 1. This is a morphism of algebras because we have a normalized hypergroup. So when you take the product of two elements from the basis, remember the sum of the coefficients that appear is always 1. So then this one is also a morphism of algebras. And based on this multiplication, you see that actually is the unit of A star, of A hat. So the question is when the dual of a normalized hypergroup, when is also a normalized hypergroup. So before formulating this, I should mention that there is a formula which computes the dual fusion coefficients written here. So basically, this formula follows from the equation of dual basis for the two pairs of dual basis. And also, if you specialize K to be 0, here you get that P0 of J1, J2 is Nj1 over Na delta J1, J2 star. So this first relation shows that we might obtain again a normalized hypergroup, because we know that this coefficient is when J1 equals J2 star, we have seen that this formal codegree Nj1 is always positive. So, well, in the next slide, I have scaled the proof for this formula, but okay, I'll go very shortly through it. So we have this formula. We have a formula for the idempotent Fk. And when I just evaluated this multiplication at Fk, On this side, I get just this coefficient because only mu k does not vanish. All the other mu's vanish. So, and expanding the formula for Fk and applying the usual pointwise multiplication, and you get that the dual fusion coefficient is exactly this formula. So the proposition that I want to mention is that the dual of any abelian normalized hypergroup is again an abelian normalized hypergroup. So somehow this class of hypergroups is closed under duality. And also here is the proof of the remaining facts. So the only more difficult fact is to show that this is also normalized, which means that the sum of the dual fusion coefficients is 1. But having a formula for these dual fusion coefficients from the previous slide, you can write this sum in this way. We recognize that this sum here is just tau, and tau is not 0 only when you evaluate it at 1 from the standard basis. So here we have a non-zero term only for a equals 1. This one is 1, h1 is also 1, and the characters evaluated at 1 is also 1. So we get that this is 1. Okay, now we can show something a little more, namely that the order of the dual hypergroup equals the order of the initial hypergroup. And this is also done using the dual basis property. So remember, the order of an element from the standard basis is defined in this way. We have formula for this thing is NA over NJ. So the order of A hat is sum of N of A over NJ, but it can easily be seen that sum of 1 over Nj is always 1, being tau of 1. Okay. Now, the problem is if we start with a probability group, which is again normalized hypergroup, but where the coefficients are, the fusion coefficients are non-negative, you don't always get a probability group. So this subclass of normalized hypergroups, the class of probability groups, is not closed under duality. So this forces us to call an abelian probability group dualizable if it happens that A hat is also a probability group. So as I already said, the only remaining condition is that the dual fusion coefficients have all to be non-negative. So out of a fusion ring, we can always construct a probability group just by normalizing the elements from the standard basis. So if I divide each element by the Frobenius-Perron dimension of the element, when the coefficient in the multiplication of A prime B prime, the coefficient of C prime, which is also denoted in this way, is the initial coefficient multiplied by this ratio of Frobenius-Perron dimensions. This is very easy to see. And the order of an element is just the product of these Frobenius-Perron dimensions. Of course, these two coincides, so it's f per dim of A square. And when you add all of them up, the order of A prime, so which is the fusion ring with being normalized as a probability group, when the order is exactly the Frobenius-Perron dimension of R. For the fusion coefficient, for the formal codegrees, in the case of a pivotal fusion category, I was able to prove that they have this ratio, dimension of C over dimension of the conjugacy class. So basically, Nj is associated to a primitive idempotent Fj, which in turn is in bijection with a conjugacy class J. Okay. Now we also need the central characters, like the usual central characters for finite groups. So these are gonna be algebra maps from the central space of elements to complex numbers given by this formula. In order to be an algebra map, one has to verify this identity, well, which is very easy to see, just well, one can verify on the standard basis given by primitive idempotence. So remember, Di is the categorical dimension of the simple object xi in the fusion category. So this is not always non-zero. But if it is non-zero, from this formula it follows that this is a character on the space of central elements. So in order to prove Burnside formula, the first step is to give a connection between structure constants and dual fusion coefficients. So we start with a pivotal fusion category in which all the i's are non-zero. Well, I should have tell you, from the Grothendieck group, you can do two things. Either a probability group, when you normalize by the Frobenius-Perron dimension, or you can get a normalized hypergroup by dividing by the quantum dimensions. So here I'm talking about the normalized hypergroup, dividing by these quantum dimensions. Of course, in the case of a pseudo-unitary fusion category, the two coincides because the quantum dimension is the same as Frobenius-Perron dimension. So the structure constants that we are interested in have this formula in terms of the dual fusion coefficients. And the proof of this formula is also based on a theorem of Shimizu. Basically, he proved this equality. If we have a character of C f of C evaluated at a character chi, class function, then we have this equality. And since we have this multiplication, so I said we normalize by quantum dimension, writing in two ways this multiplication. For example, here I apply this formula. So here I apply Shimizu equation. So I end up with this expression. While applying the definition of the multiplication, I end up with this term here. But comparing these two terms, since chi-s is the character of any simple object, through the pairing between central elements and class functions, these two terms have to coincide inside C of C. We have this equality and expand the CICJ with the structure constants. We get the formula that we like to prove, this formula. So with the help of this formula, Burnside proving Burnside the formula is just expanding the formula. Remember, we had a formula for the dual fusion coefficients in any normalized hypergroup. So we just use this formula and you get exactly the formula for the formula from the theorem. So this is P hat K and CK is related to this fact of P hat K. And you get exactly Burnside formula. So let me shortly mention that I already said this, that always there are two choices. Either you normalize by the Frobenius-Perron dimension and you get a probability group, or if possible, when all the quantum dimensions are non-zero, you get a hypergroup. But the multiplication is different. In the dual probability group, it should have been PG here for probability group. You have this multiplication, while here you have a different multiplication. So sometimes it's easier, it's better to work with Frobenius per own dimension, and other times with quantum dimension. That's why the most results which are formulated are in the case of pseudo-unitary categories, because these two dimensions coincide. So then we can put together the results from each side, Frobenius per own or quantum dimension. Okay, so now I will prove a theorem. So we have a hypergroup when we consider the basis by quantum dimension. Also, if I look at the space of central elements, I can also normalize these class sums by the dimensions of the conjugacy classes. These are objects of the Greenfield center. And I get another hypergroup generated by this class sum. So of course, as vector spaces, this is CF of C and this is CE of C. But we write hyper here to keep in mind that the standard basis is normalized by quantum dimension. So we will prove this result. For any pivotal fusion category, the dual of the class functions is isomorphic to the space of central elements, not only as algebra, but also as normalized hypergroups. So basically, I have a bijection between the normalized class sums and the characters of the dual hypergroup. And this is given by mu j is sent to the normalized class sum. And this bijection between these two sets induces a bijection at the level of the algebra between the dual of CF of C and the space of central elements. So as an example, we recover something that we already know. If you look at the dual of the character ring of a finite group with the multiplication that I have given before, this is isomorphic to the center of the group algebra. And a character of the character ring is sent in the normalized class sum. And the Shimizu equation, just to get an idea, well, we know mu j of chi I is chi I of gj, where gj is an element from the class, from the conjugacy class Cj. But since chi I is a class function, chi of gj is the same as chi I of the normalized class sum, because the dimension here is just the cardinality of the conjugacy class in this setting. So this isomorphism from here can be understood as a generalization of this fact. So, well, if I start with a normalized symmetric hypergroup, remember we have this mu0, which is the unit of A hat, but also is an algebra morphism. So it has a primitive idempotent, central primitive idempotent associated to it. It is F0 with the previous notations, but also it can be written as UA because it generalizes the notion of integral for Hopf algebras. And of course, it verifies this relation. And also from the idempotent formula, we get a formula for UA. So Harrison in 1979 have defined double cosets or quotient of probability groups in the following way. And we also need this notion. So we start with probability, it should be written group here, probability group A. Now, if I have a subgroup a probability subgroup. Sorry for this. This is at the level of the algebra generated by them. I can define an equivalence relation on the standard basis on the elements of A in the following way. Two elements are equivalent relative to S if the multiplicity of A in S1 be S2, where S1 and S2 are two arbitrary elements in S is greater than 0. So if it happens that there are two such elements, S1 and S2 in S, such that in this product, A, which is a basis element, appears with a non-zero coefficient. And it can be proven that this is equivalent with these two spaces to be equal, SAS. This is the product between any two elements, S1, A, S2, to be equal with SBS, and also, since it is an equivalent relation, it is the same as B to appear in S prime 1A, S prime 2. So this is an equivalence relation, and also Harrison proved that two elements are equivalent. We have seen already this, but this new identity we are going to use. Remember, US is the central primitive idempotent associated to mu0. So S is also a probability group. So it also has a US, an integral element. So A is equivalent to B if and only if we have this equality. So now if I take the set of all equivalence classes of S, and the vector space spanned by these equivalence classes can be written is a list as vector spaces isomorphic to UAC of A US. And then I can transfer the algebra structure from here, because this is inside C of A, to this C of A over S. And it turns out that with this algebra structure, C of A over S is also a probability group, A over S. So that's what Harrison proved in 1971, that A over S is a probability group. And also he has given a formula for the probabilities appearing in A over S. This is also, he called it a quotient of A by this subgroup S, probability subgroup. So how the formula goes? So I denote it by AS, the equivalence classes. And when I multiply two such equivalence classes, I get a linear combination. So I denote by P bar these probabilities here. They are called either fusion coefficients or probabilities. And the formula that Harrison proved is that P bar is sum of probabilities in the following way. So I choose arbitrarily, but I fix them two elements, one from the equivalence class of A and one from the equivalence class of B. And then when I make Y times Z, I take only the coefficients of all those elements that are in the equivalence class of C. So P bar is the sum of these P's from here. And a remark that we are going to use in order to prove rationality of structure constants is the following. If the initial probability group, so if this P, all the P's here are rational numbers, this P bar being the sum of these P's are also rational numbers. So in the quotient, you get also a probability group with rational numbers. And that's what we are going to do. But the question is how to get such a quotient. So also Harrison proved the following result, which basically generalizes the well-known result for a billion finite groups. So probability groups can be seen as generalization of groups. Well, basically any group is a probability group where only one element, G times H, has a non-zero coefficient. So anyway, starting with a probability subgroup S inside A, it follows first that if A is dualizable, then S is also dualizable, and moreover, the dual of S is written as the quotient between the dual of A and S perp. So you see, this is the usual isomorphism for finite abelian groups, whereas perp is the set of all characters of A, mu in A hat, which are 1 on S. And how this isomorphism goes? So an S perp equivalence class is sent to the restriction of chi at S. So this is the theorem that we are going to use. But before doing this, we also have, in the case of a modular category, we have a self-duality result. So maybe shortly I should remind you, a modular category is a premodular category that we have already seen, in which the Mueller center is trivial. Z2 of C is the category of vector spaces. So for such a category, remember IR norm is the class of irreducible characters normalized by quantum dimension. And we know that this form a normalized hypergroup. And it turns out that this is self-dual. The dual of IR normalized in this way is self, which means that at the level of algebras, the dual of CF of C is exactly CF of C. Now, if we impose, here we need a pseudo-unitary condition, then of course we said that in this condition, the hypergroup becomes a probability group. So we get that the probability group is self-dual. So in particular is dualizable. The proof of this fact is based on the Drinfeld map. The Drinfeld map of a modular category has a corresponding map at the level of characters. And Shimizu has proven also that sends characters to central elements through this formula. And moreover, it can be seen that an irreducible character is sent in this normalized class sum. Well, if I divide here by di, chi over di is sent to ci di square, but the dimension of ci is di square. So in this way, the Drinfeld maps establishes a bijection between these two sets, which in turn, extended by linearity, induces the isomorphism as algebras from here. So shortly, this is the proof of this theorem. Well, from this theorem, as a particular case, the structure constants for a modular category can be directly computed. They are rational numbers given by this formula. Di, as I already mentioned, is the quantum dimension of the simple object. And this formula is obtained from the fact that the Drinfeld map is an algebra map. So remember, we have this formula, and extending it here with the fusion coefficients, you get exactly this formula. So remember, we are interested in structure constants for premodular categories. But from here, for modular categories, we can see that actually even a stronger result can be proved. If I multiply the structure constants with the square root of dimension of C, while using this formula for the structure constants, is square root of dimension of C over dk times this product. We know that in a modular category, a stronger Frobenius property holds, namely dk square divides dimension of C. So this number from here is an algebraic integer. This is also an algebraic integer, so the product is an algebraic integer. So let me remind you from the beginning the statement of the theorem that we want to prove, that if we multiply these structure constants by dimension of C, we get algebraic integers. We've seen that in the modular case, we can replace dimension of C by square root of dimension of C. And well, if time allows, let me shortly give you an idea how to prove this theorem. So, starting with a pseudo-unitary category, it is known that the Dreyfus center is also pseudo-unitary. And also the Dreyfus center is always a modular category. So the proof of the theorem goes like this. Are there questions? Sorry. No. So I can go on with the proof.
Yeah.
Okay. So let me first establish the settings very shortly. So I start with a pseudo-unitary premodular fusion category C. We have seen the primitive idempotence of CF of C, their associated characters. So we have this equality here since the character ring CF of C is commutative. We have the conjugacy classes of C. We have a bijection between conjugacy classes and the central primitive idempotence. I also denote by M0, M1, M the set of representative of simple objects of C. Without loss of generality, M0 may be assumed to be the unit one of C. We have the forgetful functor. What is new now, I consider this forgetful functor induces a map of level of character rings. So I have F star from CF of Z of C to CF of C. And it is proven by Ettingov-Nisic and Ostri that this is a surjective algebra map. I also have to establish some notations for the Dreyfus center. Now, the simple objects of the Dreyfus center are V0, VR. So their associated primitive idempotence, I denote them with hat, E0, hat, E1. The character set chi0, hat, chi1, dimension hat. So everything coming from Z of C receives a hat to be distinguished between the same things from C. So I have the Dreyfus map from CF of Z of C to C of Z of C. Now I know that this map is an isomorphism of algebras. So when I consider the inverse of this primitive idempotence, I get also primitive idempotence here. So I denote it by the hat F of G. So proving the theorem, we need one more result, proved by Ostrich in 2015. So if I start with a spherical category, we have premodular category, so this assumption is satisfied. Ostrich showed that for any Fj, a primitive idempotent from here, there is a unique primitive idempotent in Z of C, denoted by hat phi, hat f, but sigma of j. We don't know that is the same j. Such that if I look at the restriction map F star, hat f of sigma fj is sent to fj. And moreover, the simple object V sigma of j is also a conjugacy class of C. And also the dimension of this conjugacy class equals the dimension of Cj of the initial conjugacy class, which can be written as hat B of sigma of j equal hat B of j. So I should say that for Hopf algebras, this result was proven a long time ago by Kashina and Sommerhauser and Zhou, three authors, and in this case, sigma of j equal j. And it is, well, it's not formulated, but it is kind of an open question if sigma of j equals always j. So all three results shows evidence that this happens because the dimension of these two conjugacy classes is the same. Dimension of sigma j is the same as dimension of Cj. It should have been C upper j here. Okay, so all the other primitive idempotents from Cf of 0C are sent to 0 by the restriction map. And also we know we have S matrices in premodular and modular categories. So again, to distinguish between the S matrix of 0C and that of C, we put a hat here for the S matrix of 0C. Since 0C is modular, we can also give a description of the characters of 0C, mu hat I, and on a simple object, Vj, or on the character associated to it, is given by this formula, hat Sij over hat Di, the quantum dimension of Vi. So we have a bijection between the characters of Z(C) and the simple objects of Z(C) in a modular tensor category. So the main step in the proof is, since we started with a premodular, in particular with a braided category, we have a functor, an embedding of C inside Z(C), an inclusion, and by this inclusion, every simple object of C becomes a simple object of Z(C). So I can write, remember Mi is the simple object of C, so it should be tilde I such that iota of Mi is V tilde I. The intersection between these two sets of indices is just 0, the unit of the category, because this functor has a section. If I consider the forgetful functor, F composed with I is the identity of C. So I include, if C is braided, I include it in Z of C, and then I can project back to C by the forgetful functor. Because this is identity at the level of characters, it can be written in this way. But this functor iota induces an inclusion of algebras, and in particular of probability groups that we have discussed before, between Cf of C and Cf of Z of C. And now the theorem follows in the following way. We know that Z of C is modular. So Cf of Z of C is a self-dual probability group. So in particular is a dualizable probability group. And now I can apply the results of Harrison from 1979. The dual of Cf of C is going to be the dual of Cf of Z of C over this perp. Remember the proposition proved by Harrison. And now everything is just computation. So the structure constants are related with the dual fusion coefficients. The dual fusion coefficients from here, from the theorem that we have seen before, P bar, these are the dual coefficients, are sum of dual coefficients from here. But here, since Z of C is modular, we have seen that the structure constants and also the dual coefficients, because the relation between them, they are rational numbers. So P bar from here is going to be sum of these P's. All of them are rational numbers. So basically from that remark that I mentioned earlier, all the dual coefficients here are rational numbers. And when using the connection with the structure constants, we get that they are rational numbers. So this proves that they are rational numbers, but in order to show that they multiply by dimension of C, if we multiply them by dimension of C, we get exactly integers, so one has to do more precise computations inside here. So, well, because of lack of time, I propose to skip a little bit these computations. I will just explain to you. This is the isomorphism here, so we have to compute equivalence classes here. And it turns out that these equivalence classes are given by these sets, AJ. So these are the characters that restricted, these are characters of CF of Z of C, because they have a head. When you restrict them to CF of C, you get exactly mu J. And you show that mu of sigma of J, remember sigma of J is the index from the Wostrick theorem. It should be mu of sigma of J here, like here. This is an element of AJ. And working in the formula of P bar with this element, where we know the dimensions from the Wostrick result, you get a precise formula for the structure constants. And I will go exactly to the formula for the structure constants. So here, P hat, since this is a quotient of CF of 0 C, this P, a little P hat K is sum of capital P hats. This is self-dual, so P hat equals P, because we are in a modular category. And in a modular category, we have a precise formula for P. So they are normalized by the dimensions. So we get exactly this formula. And now moving from the dual fusion coefficients to structure constants, we get this new formula for the structure constants. And moreover, here S is an index for which this is satisfied, and U an index for which this inclusion is satisfied. So putting in particular the Wostrick indices, sigma of phi and sigma of J, then you get a shorter formula for the structure constants. The formula given here, remember AK is that double coset that I have described before. And from here, we can see that if we multiply with dimension of C, I can write dimension of C CKIJ as this term times the other term. This term clearly is an algebraic integer, since these are non-negative integers, and the quantum dimension are always algebraic integers. And it is well known that the dimension of conjugacy class divides the dimension of C. So the product is the product of two algebraic integers, so therefore it is an algebraic integer. Moreover, if C is weakly integral, which means the dimension of C is an integer, then by a result of Gelaki and Nixich, it can be proven the dimension of CK is also an integer. And since this quotient is a rational number and also algebraic integer, it is an integer. Also, the head of V is an integer, being the dimension of a conjugacy class, so everything becomes an integer, proving the second part of the theorem. So this finishes the proof of the second theorem. And if you agree, in the last minutes, I will shortly present also the proof of the new result. So we say that if we multiply the joint result with Sebastian, so if we multiply with a complex number, and we get integers, like in the premodular case, then this Frobenius type property is satisfied. So the proof goes like this. So I just restated, we have to prove this fact. Now remember the Fourier transform introduced by Shimizu. He has proven that the preimage of a character is a multiple of the depotent of EI star. Now I can write chi as sum of alpha ij of j, since CF of C is assumed to be commutative. So when I apply the inverse of the Fourier transform, I obtain alpha ij cj. By definition, the preimage of the primitive depotents are the class sums. Now, alpha ij are algebraic integers, since well, they are the eigenvalues of matrices with non-negative integer entries. So these are algebraic integers. This formula from here becomes this formula, since f inverse of chi is this one from here. And now I apply the central character. Remember, we had the central character divided by di, which is not 0. So we have to make the assumption. Yes, we have to make an assumption that di is not 0 for any I. So like in the pseudo-unitary case. So applying this character here, we apply omega I star to this equation. So dimension omega I star of EI star is exactly 1, because chi I of EI is di. And here, I spend here by applying omega I star. So I get alpha ij omega I star of Cj. But going back to the structure constants, I have this formula. I multiply this formula by d squared. So I get this new formula, and applying this formula holds in the space of central characters. So applying omega I star of this formula, I get that omega I of dck, all these things are algebraic integers. Because they are eigenvalues of, again, of a matrix with algebraic integer entries. So then going back to this formula, we see that alpha ij are algebraic integers, omega I star of Cj algebraic integers. So everything is an algebraic integer, which finishes the proof. Okay, so on the last slide, I have a remark and 2 questions. So it was proven in this paper, Fourier by algebras, by Liu, Palcu, and Liu, that in the case of a unitary category, these structure constants are non-negative, not necessarily integers, but non-negative. So the questions are, if there are example of weakly integral fusion categories where these structure constants are not rational numbers. I'm not aware of such example, or an example where these are not positive. Mainly they are negative. Okay, so thank you very much. These are the references for the talk. And I will stop here. Thank you very much for your attention.
Thank you.
Okay.
So, let me ask if there are some last question.
Sure. I cannot see you any. But you can go. I should press somewhere on video too. Let me see.
Okay. Stop recording.
Here. Yes.